This is problem 10 of the QHack 2023 quantum coding challenges, and this one is entitled the super parameter. What we're being told is that, let's say we have a problem which we have implemented in the form of a quantum machine learning model, where the answer to our problem, we're told, is one of the basis states of a 3-qubit system. So it could be either state 000, 001, all the way up to 111. And, they don't give us details of what this problem is, but you could imagine that is, for example, we're trying to find the eigenstate of the ground energy of some Hamiltonian that we're given, right? So the way we would do that is we implement a model that would allow us to check through the different states we have and use gradient descent to find the minimum expectation value of that Hamiltonian, and then find the eigenstate corresponding to that ground energy, right? And the way we could implement that ansatz to generate the state is, for example, by using rotation gates with 3 different angles, right? Alpha, beta, and gamma. So if we implement an ansatz like this, where we can modify these angles, well, if we put angles of alpha, beta, and gamma equal to 0, well, that generates states 0, 0, 0, right? If we then change alpha to pi, then that will give us the state 1, 0, 0. And if we change now beta to pi and leave alpha at 0 and gamma at 0, then we get 0, 1, 0. And then we can just change these angles to different values of 0 and pi to generate all possible basis states, right? But what we're told in this problem is that even though this is a possible way to implement this ansatz, we would like to reduce the number of parameters in this model. So can we accomplish the same? Can we generate all possible basis states of the computational basis, but instead of using 3 separate parameters, can we use just 1 parameter? So replacing these 3 gates with something else that allows us to pass just 1 value here, alpha, let's say. So we wouldn't have beta and gamma. We will have just alpha everywhere in our model. Well, if we decide to keep this exact same circuit, right, with 3 Rx gates, and we just put alpha here, well, that's not expressive enough, right? Because if we change alpha from 0 to pi, then we get state 1, 1, 1, and that's it. If we replace it with pi over 2, well, we get a superposition, but we don't get precisely a basis state with some given probability. So how can we change this circuit so that we're only using 1 parameter? And if you're familiar with the Quantum Fourier Transform, it shouldn't be too hard to understand how to do this, right? So let's go ahead and take a look at the Quantum Fourier Transform and see why this is the approach we should follow to generate the circuit we need. So I'm going to be using Qiskit to help me just visualize a few things here, but this shouldn't change anything in the penny lane implementation of the circuit. It's just for us to see why the QFT is the way to go. The thing I'm going to do is from Qiskit quantum info, I'm going to import state vector, and from Qiskit circuit library, import QFT. And what I'm going to do here is I'm going to prepare a state, and then I'm going to generate a state vector for that. So state vector from, and I'm going to use this from int method that allows me to pass the state I want to prepare it with the number of elements in that state vector. So since we have 3 qubits, this will be, let's put it explicitly, 2 to the 3 elements. And then I'm gonna compute the QFT for that state just by doing psi evolve and then QFT, which I imported from the circuit library, and I need to pass the number of qubits for that QFT. So in this case, it's only 3 qubits. And now I'm going to display the state in the block sphere, which, because I'm passing basis states, it's a separable state, so I can represent them as separate qubits. And then I'm also going to display the same thing, but for the QFT, right? So if I do that, I see that for state 0, I get all 3 qubits pointing out to 0. And then the QFT has all states pointing to the state plus, right? Now, when I increase this state to state 1, well, the first qubit is going to change to 1, the other two remain at 0. And when we look at the QFT, what we see is that qubit 0 has turned from state plus by an angle of pi over 4. The second qubit has rotated by an angle of pi over 2, and the third qubit has rotated by an angle of pi. So this comes in multiples of 2, right? So if this rotated some alpha, this rotated 2 alpha, and this rotated 4 alpha. And if we see here, now I look at the second state, right? So here I have 0, 1, 0. Then we see that this now turned another pi over 4. This rotated another pi over 2, and this rotated by another pi. So it came back to the state plus. So what we can see here is that if we implement a circuit that first places all state in the plus state, right? And then rotates the first qubit by alpha, the second qubit by alpha, by 2 alpha, and the third qubit by 4 alpha. And then I perform the inverse of the QFT, then I can get any of the basis states with only one parameter alpha, right? So the final version of that circuit would look something like this, where we have at the input all qubits starting at 0. Then I can apply a QFT to that. Well, we could also just apply Hadamard gates there, because what we want after that first block is just to have them all pointing in the state plus direction. And then I apply to qubit 0 an RZ gate of 4 alpha, to qubit 1 an RZ gate of 2 alpha, and to qubit 2 an RZ gate of alpha, and then perform the inverse of the QFT. Then I can accomplish what we want, which is being able to obtain here at the output any of the possible basis states with only one parameter alpha. So as I step alpha in steps of pi over 4, then I'm going over each of the basis states at the output from 0, 0, 0 to 1, 1, 1. Now here it's important to highlight that in penny lane, qubits are ordered with the least significant qubit Q0 on the left of our state, and qubit 0 is on the top. So the fastest changing qubit here needs to be Q0, because that's the one to the left side of our state vector, in order to be stepping correctly through all the different basis states as alpha changes. Okay, so now let's go ahead and implement this in penny lane. So as usual, we import penny lane as QML, and from penny lane numpy, import it as MP. And then we're gonna create our device, which is gonna have 3 qubits. And we're gonna create our Q node, which we're gonna call model. And all we need to do now is first apply the QFT to all 3 qubits. And that's just to start, let's go back here and put state 0 here. And that's just to initialize all qubits on the state plus. So we don't need to do QFT. We could do the Hadamard gate there, but this accomplishes the same. And then we're going to apply an RZ gate of an angle of 4 alpha to wires 0, right? And then we're going to do the same thing for wires 1, but with an angle of 2 alpha. And then the same for wires 2, but with an angle of alpha. And then after that, well, we need to perform the inverse of the QFT. Now, because this is a unitary operation, the inverse is the same as the adjoint. So I can do QML adjoint and then pass QML QFT. And then I need to specify the wires. So all 3 wires in this case. And then to this, we are asked to return the probabilities on all wires. But you know, just for fun, let's actually change this from probabilities to return a state. And since we already imported what we need from Qiskit, let's try to see what this state returns. This circuit that we implemented in PennyLane returns. So if we use this state vector class in Qiskit and we pass this PennyLane Q node, and we pass, let's say, an angle of 0, so alpha equal to 0 here, and we draw the block sphere, right? So for an angle of 0, we get 0, 0, 0. And then if we change this to, let's say, pi over 4, then we get 1, 0, 0. And then if we keep increasing that to 2 pi over 4, we get 0, 1, 0. And then we should get 1, 1, 0, right? 1, 1, 0. And then if we go all the way to 7 pi over 4, we should get 1, 1, 1. So this just shows that this is working correctly. Now, the next thing that we were asked to do in this problem was to generate the coefficients necessary for this function to work. But this is exactly what we just did here. We just passed all the possible coefficients needed. But let's go ahead and do that anyway. So in the problem, they define this as a function called generate coefficients. And all we do is just create an empty list of items where we're going to just create a for loop. Actually, we can just do this as a list comprehension. Let's do coefficients. Let's do here 2 pi, right, divided by 8, right? So we have 8 possible combinations for all 2 pi rotations possible in this RZ gates, or you know, like we just said it before, we're stepping every pi over 4. So so this is the same as just pi over 4 times some I for I in range 8, and this should just return the coefficients. And if we do that and we just run this, let's see what we get. So this just gives us all the angles needed from 0 to 7 pi over 4, right? So 7 pi over 4 is this 5.49. And this is just a function that is used in this problem for the grader. But if you see here in the solution we submitted, it's exactly what we just coded. So QFT, the RZ gates, the adjoint of the QFT, then this function that generates the coefficients. And here I'm not running a test case because this just is taking something with no input and running a bunch of tests that is checking that the function is continuous, and if it's continuous a certain interval. It takes a long time to test, but I'm just showing you here that what I just coded was the one we submitted, and it was a successful submission. So I hope this was helpful, and let me know if you have any questions.